Our second lecture in this unit is called Wave Motion. The mechanical waves can be classified according to the direction of the particle motion compared to the direction of the wave motion. So we have two basic types of waves, the transverse and the longitudinal waves. We won't look at torsional. For a transverse wave, the particles move up and down through crests and troughs as we have the energy from the wave sort of travel through that medium. So on this water here, you can see that if this wave is moving to the right, the boat would be moving up and down as the water kind of transfers that wave. So for a transverse wave, we have particles that vibrate perpendicular to the direction of the wave. And when we have the wave kind of going up above that point, the equilibrium point, we have what's called a crest, and when it's going below the equilibrium point, we have what's called a trough. The other main type of wave, the longitudinal wave, we would have, because our particles move in the same direction as the wave is directed, we have periods where the particles are close together and periods where they're sort of spread apart. And we call these, when they're close together, we call that a compression. And when we have a spread apart portion, we call that a rarefaction. So for a longitudinal wave, particles vibrate parallel to the direction of the wave, and they consist of compressions and rarefactions. So just to be clear, what's being transmitted is a disturbance from the normal value of the medium, not the medium itself. The particles in the medium stay in their relative spots. They move up or down with the wave in a transverse wave, and then they'll move left or right in a longitudinal wave, but those particles generally stay where they're at. It's the disturbance that was caused by the initial vibration that's being transferred across. That energy is what's moving. Here it says when a water wave moves across an ocean or lake, it moves at a uniform speed. The water itself remains essentially in the same position. It merely moves up and down as the wave goes by. At a sporting event, you might have seen people do what's called the wave, where people in the crowd kind of stand up and they raise their arms and then they sit back down. This is not a true mechanical wave. The wave is only one-sided. It only is going up. It doesn't really go down, so there's no going below the equilibrium point. I guess the energy itself isn't really being, the medium itself isn't really a bunch of people stuck together. And with a wave, our medium is a series of particles that are kind of together as one sort of piece. So in a sports stadium, each person is not a particle of the wave or of the medium, because really each person is separate. Here is a bell jar. This is an electric ringer inside of a bell jar. So if we pump air out of that bell jar and we ring the ringer, there would be no sound, because there would be no medium for the sound to travel in. So we would have a vibration, which is the bell moving, but because there's no air to move around to cause sound, we wouldn't have any sound waves traveling. So is sound a mechanical wave? It is. And what we have with sound, when you are speaking, for example, the vibration of your vocal cords or your larynx, they cause the air near your mouth to start to vibrate, or sorry, not to vibrate, but the vibration of your larynx causes the particles in the air to start vibrating and moving up and down. And as you speak, you transfer that sound energy as a wave through the air. So that is how sound travels. So sound is a wave. It is a mechanical wave. So not only when you speak, but anytime something causes a sound to happen, the particles in either gas, solid, or liquid, they would move longitudinally, because sound is a longitudinal wave, and they would kind of have these compressions and rarefactions as they kind of vibrate along with that initial sound.